this is a rate disposal relationship. And if everyone I is equal to 5 times x, so we have a y according to this formula here, v is a continuous error, and something like the notation here. This is a metric error. Here, this is a continuous error. And so we can see the.
I think in the last one you need big V and a small V.
VI?
Yeah.
Here I don't have I here. So this represents a vector right now. If you put I here, then you need I.
No. From this one, y equal to yx plus v.
Okay. Oh yeah. This is a context so I think U is a K-sparse. So we can allocate the rate according to the sparsity. So we suppose the total rate to compare or to comprise this signal y equal to k times r, given a total rate k times r, because k is the sparsity of u, and we can consider it as the freedom of the signal, the degree freedom degree of the signal. So, given the total rate k times r, we want to figure out is that k times r is enough to recover x according to y. And before we talk this, we have some simple scenario. Suppose we have an encoder here and an encoder here, and
actually, do you mind to say again what's the role supposed to do here? Like
what's the role supposed to do here?
Yeah.
This is we have a role y hat, role y. this is the bit, this is the knowledge. Suppose we have some signal like this, but
Which one is your measurement? Y is your measurement or Y?
yeah, y is the measurement.
Okay.
Y height is quantized.
So what is B?
B is quantization error.
Oh, okay. So after you measure, you quantize it.
Yeah.
You scale before you quantize it.
Yes.
Okay.
Let's consider an encoder and a decoder. The first compression scenario is like that. Suppose the encoder has the knowledge of J. Here, J is the Here, J is the total number of combination of zero elements in U. So given small J, we want to so given a J, which want to capital J, then we can find exactly U according to U. According to UK and SJ, here SJ is the location of each non-zero element, and the UK is the non-zero k number of non-zero elements. So given a J here, we know SJ, and if we know UK, and we can recover U. If we recover U, we can figure out X, for both X is equal to So the first scenario is that suppose the encoder has knowledge of J and the decoder has knowledge of J, and the encoder has the matrix V and the decoder has matrix V. So if there are some input X, the encoder can calculate the U equal to V inverse times X. Then the encoder can get UK and SJ according to the U here. And we can compress UK and SJ and send it. We don't need to compress SJ because the decoder knows SJ already. And we only need to compress UK and send the UK to the decoder. So in this situation,
excuse me, J is equal to Sj, or J is a set of all of the indexes.
J is just index Sj is a set. Sj is a set can be chosen from.
You map between some sets to some number, and both part know about the number, and you know which sets is fired.
So if in this case we only need send UK.
Well, SG is what again?
SG is the It's a site indicate the location of the non-zero and J is the
Okay.
index. Yeah, total and J is the capital J
But
number.
your J is known.
And in this case, we only need set UK decoder, the 2 decoder. So the rate, and we suppose the total amount of bits is K times R. So the rate distortion for this scenario is just equal to C times 2 power minus 2 times R. Here the definition of
But why decoder no SJ?
why decoder also. Suppose that they know that this is a scenario 1.
Okay.
We suppose the encoder, decoder, no J, no V, and in this case, the rate of distortion is here. And the scenario 2 is encoder, no V, and decoder, no J, and the decoder only no V. So in this case, the encoder calculate U according to this formula, then get UK and SG from Q, and then send UK and SG to the decoder. In this case, decoder can decode the SG first, then recover UK and find the function of X. So I see how many bits we need to encode SG here. We know there are total number of SG is the capital G. So the total bits to encode SG is equal up to of G. This is total number of G. Suppose we have suppose J is equal to 8. Then we want to encode 8. We need 3 bits. Right?
You said bins.
Bits with BI. So we introduce R0 here, which equal to K2 and this is the total rate to compress the SG. Then suppose we have the total rate for compression is K times R. Then we have K times R minus K times R0 is for compress SK, right?
Why minus?
Because the total rate is K times R. Suppose we have total rate. Suppose the system has K times R is available to compress the source. If decoder does not have the information of SG, they should send the SG to decoder.
This must increase the rate.
No. Here we consider we will not increase the rate. Suppose the rate is constant. It's not constant, it's a certain number. In this case, we talk about the whole stuff. This is a basic assumption. The total available bits at decoder is K times R. And if we spend K times R0 bits to encode the SG, then we only have k times r minus k times r0 bits available to encode the UK here. So in this case, this option is equal to r. So we can see here that this distortion is larger than this one because we use some bits to represent the index here. And another thing we need to mention is that if R0 is larger than R, this is a trivial scenario. So we cannot, we do not have any available bits for UK. So we can just use a more simple scenario. So for this case, if R is smaller than R0, we can just spend a k times R bit to encode X directly. X is NS signal, and the total available bits is k times R. And for each symbol in the vector X, they have k times R over n bits. So this is the rate for X. So in this case, they have two conditions. If R is larger than R0, actually R should be much larger than R0, otherwise there's also trivial. Because if we only have one bit to encode UK is not enough to represent UK. And in this case, because the sigma is equal to here. Yeah, this distortion may be larger than this one. This depends on how you choose it. And so this is scenario 2. In the first two scenarios, we didn't use any information about the comparative sensing. We just compress the sparse signal directly and send it from encoder to decoder. And the first scenario suppose decoder and the encoder has the information of G, the index. And in the second scenario, G is not available at decoder. So we have the rate distortion function like this. If R is much larger than R0, then we use this distortion. Otherwise, we just directly compress the signal X. So we got two scenarios here. So let's consider if we use the comparative sensing, what's the result? Can we get a better compression rate in terms of our distortion for a given rate here if we use the compressed sensing? And so the third scenario is suppose the encoder do not have the information of B, J, they only have the information phi. The input of encoder is X here, and the encoder has the information B, J, phi, everything. This is the third scenario. Suppose encoder has the information of G. And in this case, for encoder, they can only get the information by I according to this formula, this equation. And then the encoder uses k times r bits to contact y height and send y height to the decoder. And the decoder can decode the y height according to the information of j. And in this case, we don't have a proof. We can just write down the rate distortion here. Actually, this paper did not give any proof. I tried to prove it, but I didn't get it.
Excuse me, can you explain again the scenario?
The
How
first,
an encoder can send if we don't know about the J?
the third scenario is the encoder only have the information of y, but decoder have the information of y, b, and g.
Encoder must find the sparse presentation of the signal and then send it. It's necessary to know about the J.
No. For the encoder, they don't need that information. You have talked something about that. You try to compress the image, right? Suppose the input image is x.
Oh yeah.
Yeah.
Okay.
You only need
Okay.
a random generated file here, right? So for encoder, they don't need the information of v and g. If the encoder only have the information of y, the encoder can use the compressive sensing method and use the formal quantization method to get the context version of y and assign this context version to the decoder. And with a total rate k times r. In this case, the rate distortion is equal to c times g minus r star. This is r star is equal to this equation. So we can see if encoder without the information of v, we get much higher distortion. So for the fourth scenario is the regular comparison sensing scheme. Suppose the encoder only have the information phi, and the decoder only have the information of v and phi, without the information of g here. This is the regular comparison sensing scheme. And what's the rate distortion in this case? So for this equation is the result is you cannot find the app which make the decoding is reliable. This means you cannot decode any information given this code rate. And let's see why is so. There's a theorem, and I don't know how to prove it, but I just give the result here. If here M is the mass of Y, and if you can decode signal, if you can decode the signal X according to Y, M must satisfy this constraint. Something comes from here, but I don't know how to prove it. They give many references about how to prove it. I don't have enough time to read it. And here is the theory to see if you want to decode the X variable according to the received signal Y. For a given rate K times R, M must be larger than this equation. And we can, so you cannot find such a M larger than this equation. This means you cannot get the variable decoding performance if N is approach to infinity. What I said before was based on the assumption. If N is approach to infinity, if N is not approach to infinity, you can still get some result, reliable coding performance. But if N goes to infinity, you cannot find any N that makes the decoding is reliable. So this is what the paper tried to prove. And here SNR is equal. Beta is equal to here. And we can plug beta into SNR. And another thing, we introduce a new notation here. Derivative of K over N, which represents the measurement ratio. And we can see if we increase N, we can get a more reliable. We can get more information about Y if we increase N, because the mass of Y is increased. And but the drawback is we fix the total available rate, available bits as decoder. So we increase M, it means the available bits for context each element of M is decreased, right? So suppose we have a total number of bits here, and the available bits for each variable yi is equal to this one. If we increase n, we have more information about yi. But we have less bits for to use to compare the yi. Which decrease the accuracy of Wi-Fi. And so we can see if total rate is the total bits available is K times R, we get the beta equal to here. If we
Actually, when you say infinity, I forgot you mentioned that like when n go to infinity, what happen again?
If n reach to the infinity, m cannot satisfy this equation. This means m will must be the right hand side, which means you cannot get a reliable decoding performance. Which means you cannot decode any x according to.
You mean because the right hand side go to infinity?
Yeah. No, not right hand go to infinity.
So
You cannot find that m is larger than the right hand side. Yeah, actually some part of the right hand side is go to infinity.
but n is still less. I mean, m is still less than n. Right? If m goes to infinity, the right hand side is still less than n. Right?
Yes.
I don't know what's that point of saying that thing. I mean, so n goes to infinity, then what's the problem? Like you have m, of course, goes to infinity as well, but what's the problem? I mean, what's the big deal about that?
Yeah, I also do.
Because like if you do coding, it's always like that, right? Your weight is fixed, and your n goes to infinity. Of course, you have the n goes to infinity also.
Here we suppose alpha is constant. So if n goes to infinity, k also goes to infinity.
Yeah, but what's the problem? I mean, like when you do coding, it happens like that all the time because your weight is fixed, right? When you define the weight, it's like you do define